Hello student, welcome to my channel The Learn Physics. I have already uploaded the one-shot videos of Ncert chapter 1, Ncert chapter 2, Ncert chapter 3. Today I will be discussing on Ncert chapter 4. Now our discussions are magnetic force, that is Lorentz force on a moving charge particle. Next, motion in a magnetic field, that is nature of motion of a charged particle in a magnetic field. Then combined motion in electric and magnetic field, and I will also discuss the velocity selector, the magnetic field due to current element ideal vector, that is BIOT-SAVART'S law. Then magnetic field on the axis of a circular coil. Then Ampere's circuital law, magnetic field due to toroid and solenoid, force of interaction between two parallel currents, torque acting on a coil, magnetic dipole, and finally the moving coil galvanometer, and numericals from Ncert on above topics. Okay, so let's start. Suppose a charged particle Q moves in an electric field E vector and magnetic field B vector with velocity V. Then the force acting on the charged particle Q is F vector is equal to Q E vector plus Q V vector cross B vector. Look at this force is force acting on charged particle in electric field, and this force the force acting on charged particle in magnetic field. So this force is the F force in electric plus this force is the F force in magnetic. Okay, we already discussed the force on charged particle in electric field. So now our concentration on force on the magnetic field only. Now look at this. So force on the charged particle in magnetic field. So Q is the force on the charged particle in magnetic field Q into V vector cross B vector. Therefore force is perpendicular to both velocity vector and magnetic field vector. Okay, so look at this. The magnitude of this force is the Q B V sin theta, where theta is the angle between V vector and B vector. Now the magnetic force on a charged particle Q is 0 if V equal to 0 or theta equal to 0 degree or 180 degree. That is, if a charged particle moves parallel to the magnetic field, then magnetic force is 0. That is, if V vector and B vector are parallel or anti-parallel, then magnetic force F equal to 0. Now, when V equal to 0, magnetic force is also 0. That is, magnetic force on a stationary charged particle is 0. Okay? Now, we define magnetic field. Look at this. From this equation, if Q equal to 1, V equal to 1, theta equal to 90 degree, then B equal to F. That is, when a unit charge moves with unit velocity perpendicular to the magnetic field, then force experienced by charged particle is magnetic field. So its unit, look at this, this is the Newton, this is the Coulomb, and this is the meter per second. Now Coulomb per second is the ampere, so its unit is Newton, ampere inverse, meter inverse, or in SI system it is called Tesla. Okay, so its dimension become, look at this, the dimension of magnetic field, the dimension of Newton m l t minus 2, dimension of ampere a minus 1, and dimension of meter is l minus 1. So its dimension becomes mt minus 2 a minus 1. Okay, now Tesla is a large unit, therefore smaller unit like Gauss or state are used. Now 1 Gauss equal to 1 Oersted equal to 10 to the power minus 4 Tesla. Okay, now unit of magnetic field in SI system is Tesla. So Tesla is defined as if 1 Coulomb charge moves with velocity of 1 meter per second perpendicular to the direction of magnetic field, then force experienced by charged particle is 1 Newton, then the magnetic field is called Tesla. Okay, now next. It is already known the magnetic force F equal to B Q V sin theta, where force is perpendicular to the velocity vector and force is perpendicular to the magnetic field vector. As force vector is perpendicular to the velocity vector, so force vector is no work force. Therefore, the magnitude of velocity of charged particle remain constant in magnetic field. As force is perpendicular to velocity, so it provides centripetal force for the charged particle. Therefore, trajectory of the charged particle in a magnetic field is circular. Now, maximum Lorentz force. The maximum Lorentz force F becomes BQV into sine 90 degree. That is BQV. That is when a charged particle perpendicular to the direction of velocity, then magnetic force, then Lorentz force on charged particle is maximum. Okay. Now a numerical related to Lorentz force. Look at this. A proton moves with velocity 10 to the power 6 meter per second along x-axis. Electric field is directed along y-axis and magnetic field is directed along z-axis. We have to calculate the force acting on the proton. Now look at this, charge of the proton 1.6 into 10 to the power minus 19 Coulomb. Now velocity v vector equal to 10 to the power 6 meter per second I cap, and electric field E vector equal to 10 to the power 3 volt per meter, this is the J cap, and magnetic field B vector equal to 10 to the power minus 2 Tesla into K cap. Okay. If we apply the Lorentz force, we get, look at this, this is the Q, E vector plus V vector cross B vector. Okay. Therefore, look at this. Look at this. This is the F vector is equal to 1.6 into 10 to the power minus 19. This is the 10 to the power 3 J cap, and plus, look at this, V vector cross B vector. 10 to the power 6 into 10 to the power minus 2. So this is the 10 to the power 4. Now look at this, I cross K equal to minus J. So look at this, this is the minus J. Now look at this, this is the 10 to the power 3 and this is the 10 to the power 4. So look at this. This is the 1.6 into 10 to the power minus 19 into 9 into 10 to the power 3 minus j cap. Okay. Now look at this. The net force is 1.44 into 10 to the power minus 15 Newton negative y-axis. Okay. Understood? Now next. Now force on a current carrying conductor in a magnetic field. Look at this. Suppose this is a conductor of length L, area of cross section A. This side is higher potential, this is the lower potential. So electron is moving with drift velocity Vd from this direction to this direction. Now if I be the current in a conductor, then I equal to minus N A Vd into E, where small n is the number of free electron per unit volume. Now look at this. The force experienced on each electron due to its drift velocity is minus E into Vd cross B, where B is the magnitude of magnetic field. Now look at this. The direction of magnetic field is directed inwardly. Now look at this. The total number of free electron in the conductor. Look at this. Here number of free electron per unit volume. Look at this. Here number of free electron per unit volume is small n. The volume of the conductor is A into L. So total number of free electron is A L into small n. So total force of all electron is equal to force on a conductor. So force on a conductor F equal to F vector equal to, look at this. This is the N A L into F vector. Now this is the N A L and this is the minus E Vd cross B. Look at this. Here N A Vd E negative sign. This is the L vector cross B vector. Okay. Look at this. The direction of L vector is in the direction of current. Now look at this. This is the current I. So net force on the conductor F vector equal to I L vector cross B vector. Okay. Look at this. This is the direction of drift velocity. So direction of current becomes along this direction. So direction of current this direction, direction of magnetic field inward. So direction of force, look at this. This is the upwardly. Okay, this is the F vector. Because look at this. This is the I vector. This is the B vector. So this is the force vector. Okay. Now this is the I vector, inward B vector, and this is the F vector. Understood? The direction of force is obtained from Fleming's left hand rule. In Fleming's left hand rule, if this finger represents the direction of magnetic field, this finger represents the direction of current, then this represents the direction of force experienced by the conductor. Okay. Now look at this. This is the, look at this. This is the direction of current. This is the magnetic field. So this is the force, is the upward direction. Understood? Now next. Look at this. Here the magnitude of force is equal to BIL sin theta. So magnitude of force is directly proportional to L sin theta. So force does not depend on length of the conductor. It depends on the distance between initial point and final point of the conductor. Look at this. This is the initial point. This is the final point. So this is the L sin theta. Therefore, magnetic force does not depend on length of the conductor. It depends on distance between initial point and this is the final point. So magnetic force on a closed current carrying loop is 0. Okay, understood? Now I will be solving some numerical relating to this topic. Okay, look at this Ncert numerical 4.5. Look at this, a current carrying straight conductor carries current 8 ampere in a magnetic field of 0.15 Tesla. The conductor makes an angle 30 degree with the direction of magnetic field. Now we have to calculate force per unit length on the conductor. So we know F equal to BIL sin theta. Look at this here, F by L equal to BI sin theta. Now look at this, B equal to 0.15, I equals to 8 ampere and this is the sin 30 degree. Okay, so look at this is the 0.15, this is the 8, this is the half, so this is the 0.6, this is the Newton per meter. Okay, now Ncert 4.21. Look, this is a horizontal conductor of length 0.45 meter, carries current 5 ampere. It is suspended by means of two vertical wires. The mass of the conductor is 60 gram. Now we have to calculate the magnetic field normal to the direction of current such that tension becomes 0. Now tension becomes 0 if magnetic force BIL is equal to weight of the conductor. So look at this, here BIL equal to mg. Now B is to be obtained. Now I is equal to 5, L equal to 0.45 and this is the 60 into 10 to the power minus 3 into 9.8. Okay, now look at this, here B into 5 into 45 by 100 and this equal to 60 into 9.8 into 10 to the power minus 3. Okay, now look at this and this is the 4 and this is the 3. So B equal to, look at this is the 100 into 9.8 into 10 to the power minus 3 divided by 15. Okay, now look at this is the 10 by 15 into 9.8 into 10 to the power minus 4 Tesla. This is the 6.5 into 10 to the power minus 4 Tesla. Okay, understood? Now next, if the direction of current is reversed, what will be the total tension? When direction of current is reversed, the BIL is directed along this direction. So total tension 2T is equal to twice the weight of the rod. So look at this is the 2 into 60 into 10 to the power minus 3 into 9.8 Newton. That is, look at this is the 120 gram force. Okay, no problem. Next, look at this region contains magnetic field of magnitude 1.5 Tesla directed from east to west. Radius of this region is 10 centimeter. A current carrying conductor carries current from north to south direction. If the conductor is along the axis, find magnetic force. So magnitude of magnetic force F equal to BIL. Look at this, here B equal to 1.5, I equal to 7 and L equals to, look at this is the 10, so this is the 20 centimeter, so this is the 0.2. Now look at this is the 1.5 and this is the 1.2, so this is the 2.1 Newton. Now what is the direction? Look at this, as magnetic field directed from east to west, so this is the minus I cap vector. Current from this to this direction, so this is the minus j cap vector. So look at this, the F vector is equal to IL vector cross B vector. So look at this, minus j cap cross minus I cap. So this is the minus k cap. So force is vertically downward. Understood? Now the conductor changes direction by an angle 45 degree. As the magnitude of force depends on L sin theta, that is distance between initial point and final point, as distance between initial and final point is diameter, so force becomes same. Okay? Look at this. Now the conductor moves by a distance of 6 centimeter. If the conductor moves by a distance of 6 centimeter, look at this. This is the 10 centimeter. So look at this. This length is 10 square minus 6 square under root. So this is the 8 centimeter. If this is the 8, so this is also 8. So length of the conductor inside the magnetic field is 16 centimeter, that is 0.16 meter. So force is BIL. B equal to, look at this is the 1.5, I equal to 7, so this is the 7 and this is the 0.16. Now look at this, 1.5 and this is the 1.6, so this is the 0.24 into 7 Newton. So this force 1.68 Newton. Understood? Next. Now motion of a charged particle in normal magnetic field. We know the force acting on a charged particle in normal magnetic field is F equal to BQV, as theta equal to 90 degree. Here force vector is perpendicular to the velocity vector. Okay? That is why the magnetic force is no work force. So speed of charged particle in a magnetic field remain constant and it provides centripetal force on the charged particle. So the trajectory of the charged particle in normal magnetic field is circular. Now look at this, here velocity, this is the V along this direction. If velocity V along this direction, magnetic field this direction, so look at this velocity, magnetic field inward, so force this direction. So this is the force F equal to BQV. Now at this point, now look at this velocity this direction, field inward, so force this direction. In the same way, in this point, velocity along this direction, force along this direction. In this point, velocity along this direction, force along this direction. So at all points, force is perpendicular to the velocity vector. So nature of the trajectory of the charged particle is circle. So force BQV provides centripetal force for the motion of the charged particle. If R be the radius of the circular path, then BQV equal to mv square by R. So R equal to mv by BQ. Now mv equal to P momentum by BQ. Okay. Now momentum P equal to, look at this is the under root of 2mk, where k is the kinetic energy. Now if a charged particle is accelerated by a potential difference V, then kinetic energy k equal to q into V. So look at this can be replaced by 2m q into V root under divided by BQ. So look at this, R equal to, this is the 1 by B root under of m by q into V. Okay. So the expression of radius is this and this. This formula is very important to solve the numerical relating to motion of charged particle in normal magnetic field. Okay. Now period of revolution t equal to total path divided by speed. So total path is 2 pi r divided by speed v. Now R equals to mv by bq. So look at this, this is the 2 pi and this is the mv by bq divided by v. So T equal to 2 pi m by bq. Now frequency f equal to 1 by T equal to bq by 2 pi m, bq by 2 pi m. So time period and frequency is independent of velocity of the charged particle. Okay, and this frequency is known as cyclotron frequency. So very important point, the time period or frequency of revolution of charged particle in a circular path in magnetic field does not depend on speed of the charged particle. Okay, now a numerical. Look at this, a proton charge q mass m and an alpha particle charge 2q mass 4m enter into a normal magnetic field with same a velocity, b momentum, c kinetic energy and d accelerating potential. Find ratio of radius of proton and alpha particle in each case. Now first of all, velocity. Look at this, the radius in terms of velocity is mv by bq. Look at this, here velocity same, magnetic field also same. So radius are proportionate m by q. So look at this, here rp is to r alpha equal to m by q is to 4m by 2q. So this is the 1:2. Okay, now next, when they have same momentum, so look at this, r equal to momentum p by bq. So here p constant, b constant, therefore r proportionate 1 by q. So rp is to r alpha. Look at this, charge of charge of proton is q and charge of alpha particle 2q. So this is the 2:1. Okay, now next, when they have same kinetic energy, so radius r becomes, look at this, root over 2mk by bq. Look at this, here k constant, b constant, so r proportionate root over m by q. Now look at this, rp is to r alpha. So look at this, root over m by q is to root over of 4m by 2q. So this is the 1:1. Okay, understood? Look at this, when they are accelerated with same potential difference, then look at this, the radius r becomes, look at this, 1 by b root over of 2m by q into v. Look at this, here b and v are constant. So look at this, r proportionate root over m by q. Look at this, for proton rp is to r alpha. For proton this is the root over m by q, and for alpha particle this is the 4m by 2q. So this is the 1:2. Okay, now Ncert numerical. An electron is entered into a magnetic field 6.5 into 10 to the power minus 4 Tesla with velocity 4.8 into 10 to the power 6 meter per second. What will be the nature of the trajectory of the charged particle? You know, force vector is perpendicular to velocity vector and v also perpendicular to magnetic field vector. So nature of the trajectory is circle. Now the radius of circular path mv by bq. Now put the value, m is the 9.1 into 10 to the power minus 31, b is the 4.8 into 10 to the power 6 and b is the, look at this, 6.5 into 10 to the power minus 4 and this is the q 1.6 into 10 to the power minus 19. So look at this, 9.1 into 4.8 divided by 6.5 into 1.6 into 10 to the power minus 2 meter. Okay, this is the 4.2 into 10 to the power minus 2 meter. So this is the 4.2 centimeter. Okay, no problem. Next, now Ncert 1.2. Look at this. Here data given. We have to calculate the frequency of revolution. Now frequency of revolution is BQ divided by 2 pi m. It is already known that the frequency of revolution does not depend on speed of the charge particle in magnetic field. Okay. Now what is B? B is the 6.5 into 10 to the power minus 4. Q is the 1.6 into 10 to the power minus 19, and this is the 6.28, and this is the 9.1 into 10 to the power minus 30. Now this is the 6.5, 1.6, this is the 6.28 into 9.1 to the power 8. Understood? And unit is hertz. So look at this. This is the 0.18 into 10 to the power 8 hertz. That is 18 megahertz. Okay. Suppose magnetic field is directed along x-axis. The velocity vector of the charge particle makes an angle theta with the magnetic field. The component of velocity v along x-axis is v cos theta remain constant. Now the other component v sin theta perpendicular to the magnetic field, due to this velocity the charge particle describe a circular path of radius r equal to mv sin theta divided by bq, and period of revolution t equal to 2 pi m divided by bq, because period is independent of velocity vector. Now look at this. The charge particle has two types of motion, one v cos theta and other v sin theta. The motion of the charge particle due to v sin theta is circular, and this is the straight line. So resultant motion of the charge particle becomes helix of constant pitch. What is the pitch? The distance travelled by charge particle in one complete revolution. Now what is the pitch? Pitch x equal to, this is the v cos theta into t. What is t? T is this. So this is the v cos theta into 2 pi m divided by bq. Now look at this. This is the 2 pi cos theta divided by mv sin theta, mv sin theta divided by bq, and this is also sin theta. Now this is the radius of circular path. So look at this. This is the 2 pi r cot theta. So pitch of the charge particle x equals to, look at this, either v cos theta into t or finally 2 pi r into cot theta. Okay, understood? Now motion of a charge particle in normal electric field and magnetic field, and velocity is normal to the both electric and magnetic field. Look at this. Here velocity is directed along x-axis. So look at this. V vector is equal to v I cap. Electric field is directed along y-axis. So look at this. E vector is equal to E j cap. And magnetic field B is directed along z-axis. That is B vector is equal to B k cap. Okay. Now if we apply the net force acting on a charged particle in this electric and magnetic field, we get F vector equal to Q, this is the E vector, plus V vector cross B vector. This is the E j cap, plus, look at this, this is the V I cap cross B k cap. Now look at this, I cross k equal to minus j. So look at this, this is the q into E vector minus v into b j cap. That is, the magnetic force on the charged particle is opposite to the electric force on the charged particle. Now, if velocity of the charged particle is so adjusted such that the net force F becomes 0. So look at this, for F0 E equal to V into B, therefore V equals to E into B. If the velocity of the charged particle is selected in such a way that V equal to E by B, then net force acting on the charged particle is 0. This velocity is known as velocity selector, and in this velocity the charged particle moves undeflectedly in normal electric and magnetic field. Okay, now cyclotron. Cyclotron recently out of CBSE syllabus. I just recap the formula related to cyclotron. In cyclotron, the radius of the charged particle is mv by bq, and cyclotron frequency f equal to bq divided by 2 pi m. So kinetic energy of the charged particle, look at this, Ke equal to half m v square. So look at this, this is the half m, look at this, v equal to, this is the bqr by m whole square. So look at this, this is the b square, q square, r square by 2m is the kinetic energy of the charged particle. So kinetic energy of a charged particle increases by increasing the radius of the cyclotron and the strength of magnetic field. Okay. Now BIOT-SAVART'S law. Suppose XY be a conductor carrying current I as shown in figure. Suppose DL be a very small length. According to BIOT-SAVART'S, the magnetic field due to this current is directly proportional to the small element dl. The magnetic field also proportional to current through the conductor and inversely proportional to the square of distance of the point P from the current element I dl vector. So according to BIOT-SAVART'S, dB vector proportional to I dl vector cross r cap divided by r square. Okay, now dB equal to, look at this, dB equal to mu naught by 4 pi, this is the I dl vector cross r cap divided by r square. So magnetic field at the point P perpendicular to the plane containing I dl vector and r vector, here directed inwardly, and here now mu naught equal to 4 pi into 10 to the power minus 7 Weber per ampere meter is the permeability of the free space. Now look at this, here dB equal to mu naught by 4 pi, this is the IDL sin theta divided by r square. Look at this, here sin theta is the angle between ideal vector and r vector. Okay, so look at this, this is, look at this, this is the scalar form of BIOT-SAVART'S law, this is the vector form of BIOT-SAVART'S law. Okay, now similarity of BIOT-SAVART'S law for magnetic field and Coulomb's law for electric field. Look at this, both are inversely proportional to square of distance. Number 2, both are long range. Number 3, both obeys the principle of superposition. Now look at this. The electric field produced due to scalar source, that is charge, whereas the magnetic field is produced due to an ideal vector which is a vector source. Number 2, electric field is the displacement vector, that is electric field directed along or towards the charge, but magnetic field is normal to the plane containing the source and r vector. Okay, now finally the electric field does not depend on angle, but magnetic field depends on angle between ideal vector and r vector. Okay, now a numerical. An element delta L equal to delta x I cap is placed at the origin, I equal to 10 ampere. Find magnetic field on the y-axis at a distance of 0.5 meter. Now look at this. This is the x-axis. Okay, this is the origin. We have to, this is the current element here, current element delta x I cap. We have to calculate magnetic field R at a distance 0.5 meter on y-axis. Now look at this. Here I delta L vector is equal to 10 into delta L equal to 1 centimeter. So 1 by 100. This is the I cap. Okay. So this is the 0.1 I cap. Now R vector is equal to 0.5 J cap meter. Now we have to calculate magnetic field. So look at this dB vector, this equal to mu naught by 4 pi. This is the ideal vector cross r cap divided by r square. Okay. Now look at this. Now look at this, I cross j equal to k. So look at this, this is the 10 to the power minus 7 and this is the 0.1 k cap divided by 0.5 whole square. Okay, no problem. Now look at this, this is the 10 to the power minus 8 divided by 0.25 k cap. This is 4 into 10 to the power minus 8 k cap Tesla. Understood? Next, look at this. This is a straight conductor carrying current I. The magnetic field at a distance capital R from straight conductor at the point P is given by dB equal to mu naught by 4 pi I by R into sin theta 1 plus sin theta 2. The direction of magnetic field is the perpendicular to the plane of the board and directed inwardly. Okay, for infinitely long straight conductor, both theta 1 and theta 2 equal to 90 degree. So for an infinitely long straight conductor, magnetic field B, this equals to mu naught by 4 pi and this is the 2I by R. So this is the mu naught I divided by 2 pi R. Now magnetic field at one end of a infinite long straight conductor, in this case either theta 1 or theta 2 equal to 0 and other angle is 90 degree. So look at this, here B equals to, this is the mu naught by 4 pi, this is the I by R. So here mu naught I divided by 4 pi R. Okay, understood? Now next, suppose this is a circular coil carrying a current I as shown in figure. We have to calculate the magnetic field at the center. According to BIOT-SAVART'S law, the magnetic field at the center dB vector, this equal to mu naught by 4 pi. This is the ideal vector cross r cap divided by r square. Here angle between r vector and ideal vector is 90 degree. The magnetic field at the center is perpendicular to the plane of the board and directed outwardly. Okay. Now Now the angle between r vector and ideal vector is 90 degree. So look at this, dB equal to mu naught by 4 pi. This is the ideal sine 90 degree divided by r square. Okay, now B equal to integration of mu naught by 4 pi. This is the ideal by r square, limit 0 to 2 pi r. So this becomes mu naught by 4 pi. This is the I into 2 pi r divided by r square. So here B equal to mu naught I divided by 2r. Okay. For a semicircular coil, the magnetic field become half of this. Now look at this. This is a arc. This arc makes an angle theta at the center. Now magnetic field at the center is equal to theta divided by 2 pi into mu naught I by 2r. Okay? Understood? Look at this. This is a circular coil of radius capital R carrying current I in a anti-clockwise direction. We have to calculate the magnetic field on the axis of the circular coil, that is on the x-axis. That is, the coil is on the yz plane. Now consider current element ideal vector at this point and another ideal vector at the diametrical opposite point. Now look at this, the magnetic field at the point P due to this current element ideal vector is dB vector equal to mu naught by 4 pi. This is the ideal vector cross r cap divided by r square, where this is the r vector. Okay. Now look at this. This is the x. Look at this. This is the x. This is the r. So r equal to root under of r square plus x square. Now the direction of magnetic field at this point is perpendicular to r and also perpendicular to ideal vector. So this is the dB. Okay. In the same way, the magnetic field due to this current element is also directed along this direction. Okay. Now look at this. The angle between smaller and ideal vector is 90 degree. So look at this, dB equal to mu naught by 4 pi. This is the ideal sine 90 degree divided by r square. Okay. So this is the dB equal to mu naught by 4 pi. This is the ideal by r square. Now suppose this angle theta. Okay, a perpendicular is drawn on x-axis. If this is theta, so this is 90 minus theta, so this is theta. Now look at this. So component of dB along this direction is dB cos theta and here dB sin theta. In the same way, look at this. This angle theta, so this also theta. Here dB, this is the dB cos theta and this is the dB sin theta, so 2 dB sin theta. Now there are millions of current element on this point. So due to this current element, the magnetic field perpendicular to the x-axis becomes 0 and magnetic field along the x-axis is added. So net magnetic field along the x-axis B equal to, look at this, integration of dB sin theta from limit 0 to 2 pi capital R. Okay. Now look at this. Here sin theta equal to perpendicular by hypotenuse. So look at this. This is the 0 to 2 pi r. And now dB equal to mu naught by 4 pi. This is the ideal by r square into capital R by small r. So look at this. This is the mu naught I capital R by 4 pi epsilon naught small r cube integration dl 0 to 2 pi r. Now B equal to, look at this, this is the mu naught by 4 pi, this is the 2 pi r square into I, this is the r cube, okay. So look at this, this is the area of the coil. So this is the mu naught by 4 pi, this is the 2ai by capital R cube. If proton number of turn in the circular coil be capital N, then look at this, B equal to, this is the B equal to mu naught by 4 pi, and this is the 2NAI divided by R cube, where NAI is the magnetic moment due to the circular coil. So this equal to mu naught by 4 pi, this is the 2m by capital R cube, where small m equal to NAI is the magnetic moment due to circular coil. So a current carrying coil behaves as a magnet having magnetic moment NAI. The anticlockwise current produces north pole and clockwise current produces south pole. Now look at this numerical 4.14. Look at this, this is the coil X carries current in anti-clockwise direction, number of turn this, radius this, and current carrying this. Now coil Y carries current in clockwise direction, number of turn this, current 18 ampere and radius 0.10 meter. Now we have to calculate magnitude and direction of magnetic field for an observer who looks due west. Now for this observer, the magnetic field of this coil is directed towards east, and for this coil is directed towards west. So net magnetic field B is equal to B2 minus B1. So B2 equal to mu naught N2 I2 divided by 2R, okay. And due to this coil, look at this, this is the mu naught, this is the N1 I1 by 2R1, this is the R2. Now look at this, mu naught is common, look at this N2, N2 means 25, I2 is equal to 18 and R2 into 0.1 minus, look at this, N1 is 20, this is the I1 is 16 and radius 2 into R1, so this is the 0.16, okay, no problem. Now look at this, this is the 4 pi into 10 to the power minus 7. Now look at this, this is the 9 into 25, so 225, and this is the 0.1, so this is the 2250. Now look at this and this is the 100. Now this and this is the 10, so this is the 1000, okay. Now look at this 2250 minus 1000, so this is the 4 pi into 10 to the power minus 7 into 1250. So look at this, this is the 4 pi into 1.25 into 10 to the power minus 4. Look at this, this is the 5 pi. So 5 pi into 10 to the power minus 4 Tesla is the magnitude of magnetic field directed along west, okay, understood. Now next, Ampere's circuital law. The line integral of magnetic field around a closed loop is mu naught times the current enclosed by the loop. Now look at this, this is a closed loop, current enclosed by the loop is I, this is the magnetic field. So line integral of magnetic field is B vector dot dl vector, this is equal to mu naught times I, okay. Therefore line integral of magnetic field around a closed loop is mu naught times the current enclosed by the loop, where mu naught is the permeability in the free space. Now proof of this law. Suppose look at this, this is a infinitely long straight conductor, okay. This is a circular loop of radius capital R. Now magnetic field at this point B equal to mu naught I divided by 2 pi r. The magnetic field at this point is normal to the board and directed inwardly. Therefore, at any point of the circular loop, the magnetic field is uniform in magnitude and directed tangentially. Therefore, B vector parallel at dl vector. So look at this, the line integral of magnetic field B vector dot dl vector. This is line integral B dl cos 0 degree because B vector and dl vector are parallel. Now look at this. This is the, as B is uniform in magnitude, so this is the line integral of dl. Now length of the circular loop of radius r is 2 pi r, so this is the B into 2 pi r. Now magnetic field B equal to, look at this, this is the mu naught I by 2 pi r and this is also 2 pi r, therefore this is the mu naught I. Okay, understood? Now limitations of Ampere's circuital law. During charging and discharging of a capacitor, magnetic field produced in it. This magnetic field is not obtained with the help of Ampere's circuital law. Okay? Now we have to calculate the magnetic field in a solenoid. Look at this. This is the half section of a portion of a solenoid. Now the cross represents incoming current and this is the outgoing current. Now the magnetic field on the axis of the solenoid, look at this, due to incoming current is directed along this direction, and magnetic field due to outgoing current, look at this, this is the direction of current and magnetic field along the axis also along same this direction. Okay. Now look at this, the magnetic field at this point due to this current, look at this, is directed along this direction. So magnetic field along this direction. Now due to this current is directed along this direction. Now the net magnetic field in this point is 0. In the same way, look at this, the magnetic field at this point due to this current is this direction and this current is this direction. So net magnetic field outside the solenoid, the net magnetic field outside the solenoid is 0. Now number of turn per unit length is small n. Now consider a rectangular loop P, Q, R, S. Where, look at this, this is the H. Okay, and its one side PQ is on the axis of the solenoid. Now the line integral of magnetic field of the rectangular loop P, Q, R, S, this is equal to, look at this, this is a B vector dot dl vector from P to Q plus, look at this, B vector dot dl vector from Q to R plus B vector dot dl vector, B vector dot dl vector from R to S plus B vector dot dl vector from S to P. Okay. Now look at this. Look at this, between QR and SP, the B vector and dl vector are perpendicular to each other. So B vector dot dl vector is 0. So look at this portion and this is also 0. Now magnetic field outside the solenoid is also 0. Therefore this term also 0. So look at this, this is the P to Q, here B vector dot dl vector, look at this, plus 0, look at this, plus 0. Okay. So here B into dl means length of this, so B into H. Now look at this, number of turn per unit length is n. So number of turn in the length H is n into H. So current in NH turn is NHI. So current enclosed by the loop is NHI. So look at this, here B into H equal to mu naught N H I. Therefore, B equal to mu naught Ni is the magnetic field due to a solenoid. At one end of a solenoid, magnetic field becomes half of this magnetic field. Okay, next. Look at this Ncert numerical 4.8. The length of a solenoid is 80 centimeter. It has 5 layers. Capital N equal to 400 turns per layer. Current I equal to 8 ampere. Now we have to calculate magnetic field on the axis of a solenoid at the center of the solenoid. Now look at this. Here number of turn per unit length, this is the N by L. So this is the 400 divided by 0.8. So look at this. This is the 500 per meter. Okay. Magnetic field due to each layer is mu naught Ni. So look at this. This is the 4 pi into 10 to the power minus 7. This is the 500 and this is the 8. So look at this. This is the 2000 pi into 8 into 10 to the power minus 7. So look at this. This is the 16 pi into 10 to the power minus 4 Tesla. As it has 5 layers, so total magnetic field is 5 times of this. So B dash is equal to 5B. So look at this. This is the 5 into 16 pi into 10 to the power minus 4 Tesla. So this is the 80 pi into 10 to the power minus 4 Tesla. So this is the 8 pi into 10 to the power minus 3 Tesla. Therefore 8 pi milli Tesla. Okay, understood? Now next, look at this. This solenoid is on a horizontal plane. A wire of length 2 centimeter is placed normal to the axis of the solenoid. Its weight is 2.5 gram. Now we have to calculate the current in the solenoid I naught to support this wire. Now we have to calculate the magnetic field in the solenoid. Now look at this. Here B equal to, the magnetic field inside the solenoid along its axis, B equal to mu naught Ni. As it has 3 layers, so magnetic field in this solenoid is 3 into mu naught Ni. Here I equal to I naught. Now magnetic field, this is the 3 into 4 pi into 10 to the power minus 7. And now look at this number of turn per unit length. Total number of turn 300 and length is 0.6. So this is the 300 divided by 0.6 into I naught. Now look at this. This is the 12 pi into 10 to the power minus 7 into 500 I naught. Okay. Now look at this. 500 into 12. So this is the 6000 pi into 10 to the power minus 7 I. Okay. Now this is the 6 pi into 10 to the power minus 4 into I naught. Okay. As this wire is equilibrium, so now this wire of length L equal to 2 into 10 to the power minus 2 meter, carrying current I equal to 6 ampere and weight M equal to 2.5 gram will be equilibrium if weight mg is equal to the forces, the weight mg equal to magnetic force BIL. Now look at this. This is the B. We have to calculate now this is the B, this is the I and this is the L. Okay, and this is the mg. So here look at this. Here BIL equal to mg. Now B equal to 6 pi into 10 to the power minus 4 I naught, current through the solenoid. I is equal to 6 ampere. L is equal to 2 into 10 to the power minus 2 meter and M is 2.5 gram converted to kg 3 and this is the 9.8. Okay. Now look at this. This is the 12. So this is the 72 pi into 10 to the power minus 6 I naught, and this is the, look at this, this is the 2.5 and 9.8, so this is the 2.45 into 10 to the power minus 2. Now I naught equal to, look at this, 2.45 into 10 to the power minus 2 and 10 to the power minus 6, so this is the plus 6, and this is the 72 pi. This is 24500 divided by 72 pi, so this equals to 108 ampere. Okay, understood? Now we have to calculate the magnetic field due to a toroid. Toroid is a circular solenoid, that is two ends of the solenoid are connected. Now this is the half section of the toroid. Look at this, this is the inner radius, this is the outer radius. Now here current enter in this point and current leaves from this point. Okay, now this is the inner radius and this is the outer radius. So mean radius capital R is equal to R1 plus R2 divided by 2. Now due to this current, magnetic field at this point is directed along this direction, that is axis of the toroid. Now look at this, due to this current is also this direction. In the same way, here magnetic field along this direction, here this direction, here this direction. So look at this, the magnetic field on the axis of the toroid is directed tangentially. See, therefore B vector parallel at dl vector. Now applying Ampere's circuital law, the B vector dot dl vector, this is equal to mu naught. If the total number of turns in the toroid be capital N, so current enclosed by the toroid is equal to Ni. Look at this, here B dl cos 0 degree, this is mu naught Ni. So here B into closed integral dl, this is the mu naught Ni. Now B equal to, now B into 2 pi r, this equal to mu naught Ni. Therefore B equal to mu naught N divided by 2 pi capital Ri. Now look at this, total number of turn divided by length of the axis. So this is the number of turn per unit length. Therefore this is the mu naught Ni is the magnetic field due to toroid. Okay, now look at this 4.17 of Ncert. Here inner and outer radius of a toroid, this is the 25 centimeter and 26 centimeter. So mean radius of the toroid is 25.5 centimeter. Total number of turn is 3500. Now current I equal to 11 ampere. Now we have to calculate magnetic field outside the toroid. We know the magnetic field outside the toroid is 0. The magnetic field around the toroid, the magnetic field around the toroid is also 0. Now will the magnetic field in the toroid be uniform? No, the magnetic field in the toroid is not uniform. From inner radii 25 centimeter to 26 centimeter. So there is a slight variation of magnetic field. Okay. Now we have to calculate the magnetic field on the axis of the toroid. Look at this. This is the B equal to mu naught Ni. What is N? N equal to capital N divided by 2 pi r. Now N equals to 3500. Now this is the 2 pi. R equals to 25.5 centimeter, so it should be converted to meter, 10 to the power minus 2. So look at this, this is the 350000 and this is the 51 pi. Okay, now magnetic field B equal to, this is the 4 pi into 10 to the power minus 7. Look at this, N equals to 350000 divided by 51 pi. And this is the 11. So this is the magnetic field due to toroid. Okay. Now we have to calculate the magnetic field due to infinitely long straight thick conductor. Now look at this. This is a part of a infinitely long straight conductor of radius capital R and carrying a current I as shown. Now we have to calculate magnetic field at the point P at a distance small r, and we also calculate magnetic field when R equal to capital R and R less than capital R. Now first of all, when the point P is outside the conductor, look at this. This is a Amperian loop. The magnetic field on the Amperian circular loop of radius r and center is at the axis of the toroid is uniform in magnitude and directed tangentially. So here B vector parallel dl vector. Now applying Ampere's circuital law, B vector dot dl vector, this equal to mu naught. Look at this. This is the current to the conductor is I. So the current enclosed by the loop is also I. So this is the mu naught I. So here B dl cos 0 degree and this is the mu naught I. So here B, as B is uniform, so here B loop integral dl equal to mu naught I. Now B into this is the 2 pi smaller into mu naught I. So B equal to mu naught I divided by 2 pi r. Therefore B proportionate 1 by r. When small r equal to capital R, that is P on the surface of the conductor, then radius of the loop becomes capital R. If radius of the loop becomes capital R, then the current enclosed by the loop is also I. So magnetic field on the surface of the conductor is B proportionate 1 by small r replaced by 1 by capital R. Understood? Now next, the magnetic field inside the conductor. Look at this. Here radius small r is less than the capital R. So current enclosed by the loop, look at this, I dash equals to I divided by pi capital R square into small r square. So I small r square divided by capital R square. Now applying Ampere's circuital loop, B vector dot dl vector closed integral into I r square by capital R square. Now look at this. This is the B into 2 pi r. This is the mu naught r square by capital R square. So finally we get B equal to mu naught I r divided by 2 pi capital R square. So here B proportionate R. Therefore magnetic field inside the conductor B proportionate R and outside it B proportionate 1 by R. If a graph is plotted between R and B, the graph is straight line within the conductor as B proportionate R, okay? And outside the conductor as B proportionate 1 by R, so it is a curved line, okay? Understood? Now next. Suppose I be a current through a straight thick conductor of radius capital R. Now we have to calculate the ratio of magnetic field at R equal to R by 2 and at R equal to 2R. Now look at this first case. Look at this, B1 is equal to mu naught I small r divided by 2 pi R square. So look at this. This is the mu naught I, this is the R by 2 and 2 pi R square. So look at this, this is the mu naught I by 4 pi R, okay? Now what is B2? Now B2 equal to mu naught I divided by 2 pi small r. So mu naught I divided by 2 pi, this is the 2R. So this is the mu naught I divided by 4 pi R, okay? Therefore B1 is to B2, this is the 1 is to 1, okay? Understood? Now next. Now we have to calculate the force of interaction between two parallel currents. Now look at these two parallel straight conductor carrying current I1 and I2. Now the magnetic field at Q, this is the BQ equal to mu naught I divided by 2 pi r. And this magnetic field is directed inwardly. The force experienced by this conductor due to this magnetic field F2 equal to, this is the BQ, this is the I2 into L, where L is the length of the conductor. Now the direction of this force is directed towards P. So this is the force F2. Okay. Now F2 equal to, this is the mu naught I1 I2 L divided by 2 pi r. Okay. In the same way, the force experienced by this conductor in this magnetic field F1 is equal to mu naught I1 I2 L divided by 2 pi r, and this force is directed towards this direction. So two parallel current flowing in same direction, that is two like current attracts each other. Therefore F1 equal to minus F2, and two unlike current, two parallel current flowing in opposite direction repel each other. That is two unlike currents repel each other. Okay. Now a definition of ampere. Look at this. If I1 equal to I2 equal to 1, L equal to 1 meter, R equals to 1 meter, then F1 equal to 2 into mu naught by 4 pi. So this is the 2 into 10 to the power minus 7. Okay. If two parallel conductors are separated by a distance of 1 meter in free space, then the unit current in each conductor, by which unit length of each conductor experiences the force of 2 into 10 to the power minus 7 Newton per meter, then current in each conductor is called ampere. Okay. Now look at this Ncert 4.7. Straight conductor NB carries current 8 ampere and 5 ampere. Separated by a distance of 4 centimeter, we have to calculate the force acting on 10 centimeter length of this conductor. Now look at this, the force experienced by, look at this is the mu naught I1 I2 L divided by 2 pi capital R. Now look at this is the 4 pi into 10 to the power minus 7, I1 is 8, I2 is 5, L is, look at this, 10 centimeter. So this is the 10 by 100, and this is the 2 pi r equals to 4 into 10 to the power minus 2. Okay. This is the 80 into 10 to the power minus 6, and this is the 4. So this is the 20 into 10 to the power minus 6. So this is the 2 into 10 to the power minus 5 Newton. Okay. Understood? Now we have to calculate the torque acting on a rectangular coil. Suppose PQRS be a rectangular coil having length PQ equal to RS equal to L, and breadth QR equal to PS equal to B. Current carrying in the, now current in this coil is I. Now look at this, the force experienced by PQ in this magnetic field, this is the BIL, and according to Fleming's left hand rule, this force is directed inwardly. So this is the F1. Okay. In the same way, the force experienced by RS is F2 equal to, look at this also BIL, and this is directed outwardly. Okay. Now the force experienced by QR and PS is 0 because they are parallel to the magnetic field. Now look at this, these forces F1 and F2 are equal, opposite and parallel. So they constitute a couple. The moment of the couple tau equal to BIL into distance between them. Distance between them is the breadth. So this is the B. So this is the BIA. is the torque experienced by the coil. Look at this, if N be the number of turns in the coil, so torque tau equal to, this is the BINA. So maximum torque, so torque acting on the coil is BINA. Okay, the torque acting on the coil is BINA, that is BINA. Okay, now look at this, NAI into B. So this is the M into B. In terms of tau vector, this is the magnetic moment M vector cross B vector. So tau vector equal to M vector cross B vector. Okay. Now Ncert 4.9. Look at this. The area of a square coil is equal to 0.01 meter square. It carries a current of 12 ampere. The normal of the coil makes an angle 30 degree with the magnetic field. We have to calculate torque. Now look at this, we know tau vector equal to M vector cross B vector. Now this is the tau equal to MB sin theta. Now look at this, M equal to NAIB sin theta. So look at this, this is the BINA, BINA sin theta. Here number of turn N equal to 20. So look at this, B is the 0.8. What is I? I equal to 12, N equal to 20 and area A equal to 0.01 and this is the sine 30 degree. Okay, this is the 9.6, this is the 0.2 and this is the half. So this is the 0.96 Newton meter is torque experienced by the square coil. Okay, understood? Now 4.25. A circular coil of radius 10 cm carrying current 5 ampere and its number of turn N. It is placed normal to the magnetic field. So angle between magnetic moment vector or area vector and B vector is 0. And now look at this, B equals to 1 Tesla. Find the torque. As theta 0, torque acting on it is BINA sin theta. Sin theta 0, so torque 0. Now force acting on the coil. We know the force acting on a closed loop is 0, so force acting on the coil is 0. Now what is the force experienced by each electron? Now to calculate the force on each electron, we have to calculate the drift velocity. So drift velocity Vd equal to I by NAE. I equal to 5 ampere, N equals to 10 to the power 29 and A equals to 10 to the power minus 5 and charge of electron 1.6 and charge of electron 10 to the power minus 90. Now look at this, 29 minus 5, 24, 24 minus 19, so this is the 5. So look at this, this is the 5 by 1.6 into 10 to the power minus 5. Okay. Now force. Now force F equals to B Q V. B equals to, look at this, this is the 0.1 Tesla. This is the charge of electron 1.6 in 10 to the power minus 19 coulomb. B equal to 5 into 10 to the power minus 5 by 1.6. Okay, this cancel out. This is the 5 into 10 to the power minus 25 Newton. Okay, understood? Now circular coil act as a magnetic dipole for a long distance. Now the magnetic field on the axis of the circular coil B equals to mu naught by 4 pi and this is the 2m divided by is the r square plus x square to the power 3 by 2. Look at this, if x is greater than r, that is for long distance. Look at this becomes mu naught by 4 pi, this is the 2m divided by x cube. Because x is greater than r, so r square is negligibly small in comparison to x square. Now electric field on the axis of a dipole is, look at this is the 1 by 4 pi epsilon naught 2p by x cube. Here p is the electric dipole moment, Here m is the magnetic dipole moment. The nature of expression are same, only differ by their constant. Okay. So current carrying circular coil is treated as a magnetic dipole for long distance. Understood? Now Bohr magneton. If a electron rotates in a circular path, it constitutes current. What is the current? The current I equal to charge by period of revolution. If v is the speed of electron in circular path, then T equal to 2 pi r by v. So current is equal to EV divided by 2 pi r. Now magnetic moment in the coil due to orbital electron is m equal to, this is the AI. A is the pi r square and I equal to EV by 2 pi r. So this is the half EVR. So magnetic moment due to orbital electron m equal to half VR. Now according to Bohr's second postulate, the angular momentum mvr equal to nh by 2 pi. Okay. So magnetic moment m equal to half E into Vr. So Vr equals to nh divided by 2 pi m. Okay. So this is the He by 4 pi m into n. Therefore magnetic moment produced due to orbital electron is n times the He by 4 pi m. This is known as, now this is this is n into mu b, where mu b is equal to He divided by 4 pi m is called Bohr magneton. The magnitude of Bohr magneton is 9.27 into 10 to the power minus 24 joule per Tesla. Now moving coil galvanometer. The main parts of the moving coil galvanometer, this is the rectangular coil of insulated wire. This is the phosphor bronze strip. This is the mirror M. This mirror measures the angle of twist. This is the torsion head T, and this is the north pole and south pole of a strong magnet, and the pole pieces are cylindrical in shape such that the magnetic field in the coil becomes radial, and this is the hairspring. Okay. Now when I current passes through the coil, the torque produced in the coil, this is the B now, where B is the strength of magnetic field, I be the current through the coil, N be the number of turn, and A be the area of the coil. Here theta is equal to 90 degree because the magnetic field is radial. Due to this torque, this coil start rotating. The elasticity of phosphor bond strip try to opposite. Now if be the torsional constant per unit twist be C, then C theta equal to B now, where theta is the angle of twist and C is the torsional constant per unit angle of twist. So I equal to C divided by NBA into theta. Now this term is known as K galvanometer constant. This is the I. Therefore the current passes through the coil is directly proportional to angle of twist of the phosphor bronze strip. This angle of twist is measured by the mirror with the help of lamp and scale arrangement. Okay, and this is the highly sensitive instrument. Okay, now current sensitivity. Current sensitivity is the angle of twist for unit current. So current sensitivity theta by I, look at this, theta by I equals to NBA divided by C, and voltage sensitivity theta by V equal to theta by I into R. So this is the NBA divided by CR. Both voltage sensitivity and current sensitivity can be increased by increasing the strength of magnetic field or decreasing the torsional constant per unit angle of twist. That is why to decrease the C, we use the phosphor bronze strip instead of phosphor bronze wire, and the coil is placed between the two pole pieces of a strong electromagnet. Okay, now 4.10. We have to measure the ratio between current sensitivity and voltage sensitivity of two galvanometer having these specification. Now, first of all, current sensitivity theta by I, this equal to NBA by C. Now, look at this. The current sensitivity of first divided by current sensitivity of second, this equal to, look at this, N1 by N2 into B1 by B2 into A1 by A2. Now put the values. Look at this. First of all, N1 by N2. So this is 30 divided by 42. Look at this, B1 by B2. So look at this. This is the 0.25 by 0.50. Okay. And A1 by A2. Look at this. A1 equal to, this is the 3.6 into 10 to the power minus 3 divided by 1.8 into 10 to the power minus 3. Okay, no problem. Now look at this. This and these two. This and these two. Now 2 cancel out. So look at this. This is the 30 divided by 42. So here this is the 15 by 21. So this is the 5 by 7. So ratio between current sensitivity of this galvanometer and this galvanometer is 5:7. Okay. Now voltage sensitivity. Look at this. The voltage sensitivity theta by V equal to NBA divided by C into R. Now theta by V of first is to theta by V of second. Look at this. This is the N1 by N2. This into B1 by B2. And this is A1 by A2. And finally, look at this. This is the R2 by R1. Both have same torsional constant. Now put the value. N1 by N2. Look at this. This is the 30 divided by, this is the 42. Now B1 by B2. 0.25 divided by 0.50. A1 by A2, look at this, 3.6 into 10 to the power minus 3 divided by 1.8 into 10 to the power minus 3, and finally R2 by R1, so 14 by 10. So this is the 14 divided by 10. Okay, now look at this and this, 10, 14. Okay, so 10 by 14, this is the 2, this 2, so 2 cancel out. This is the 14 by 10. So this is the 1 by 1. Okay. Ratio of voltage sensitivity is 1:1. Okay. Understood? Now next. Now the increase of range of ammeter. Suppose an ammeter of resistance capital G measures the current Ig in full scale deflection condition. Now we have to measure the current I equal to N into Ig by this ammeter. So to measure this current, a weak shunt S is connected with the ammeter such that the rest of the current I minus Ig passes through the shunt. Now look at this. Now applying the formula Ig equal to I into S divided by S plus G. Look at this. Here I equal to N into Ig. So look at this. This is the Ig and this is the N into Ig into S divided by S plus G. Now Ig cancel out. So Ns equal to S plus G. So this is the N minus 1 into S divided by G. So S equals to G divided by N minus 1. Okay. So required shunt is equal to G divided by n minus 1. Okay, and look at this, the dotted line represents the total ammeter circuit. Okay, now next. Now increase the range of a voltmeter. Suppose a voltmeter measures the voltage Vg equal to Ig into G in full scale deflection condition. Now we have to measure the potential difference V equal to N into Vg. So to measure this voltage, a high resistance in series is connected with the voltmeter. Now look at this. This is the high resistance, capital R is connected with it to measure V such that current becomes unchanged, that is Ig. So, and this dotted line represents the total voltmeter circuit. Okay. Now look at this. Here Ig equal to V divided by total resistance. What is the total resistance? G plus R. So look at this. This is the G plus R. Now put the value of V. This is the V into N into Vg divided by G plus R. Now Vg equal to Ig into G. So look at this. This is the Ig and this is the N into Ig into G divided by G plus R. Okay. Now Ig cancel out. So look at this. This is the R plus G equal to N into capital G. So R equal to G into N minus 1 is the required resistance connected in series with the voltmeter to increase its range by N times. Okay. Now look at this 4.27. The resistance of a galvanometer is 12 ohm and full scale deflection current is 3 into 10 to the power minus 3 ampere. Now we have to measure the voltage 18 volt. What will be the resistance connected in series with the galvanometer? Now look at this. So voltage measured by the galvanometer is Ig into G. So this is the 3 into 12 into 10 to the power minus 3. So this is the 36 into 10 to the power minus 3 volt. Now the voltage to be measured V equal to 18 volt. Now N equal to V by Vg. So look at this. This is the 18 divided by 36 into 10 to the power 3. So look at this. This is the 500. Now resistance in series connected with the galvanometer R equal to, this is the G into N minus 1. Now look at this. G is the 12 and this is the 500 minus 1. Now 500 minus 1. So this is the 6000 minus 12. So this is the 5988 ohm. Okay. Understood? Now look at this 4.28. The resistance of a galvanometer is 15 ohm. The full scale deflection current is 4 milliammeter. The full scale deflection current is 4 milliampere. Now find the value of shunt such that it measures the current 6 ampere. Now we have to calculate the value of N. N equal to I by Ig. So look at this. This is the 6 by 4 into 10 to the power minus 3. So 6000 divided by 4. So this is the 1500. Okay. Understood? Now the required shunt S equals to G divided by N minus 1. Now look at this. This is the 15 ohm and this is the 1500 minus 1. So this is the almost 1 by 100. So this is the 10 milli ohm. Okay. Understood? Many thanks for watching this video. I hope this video will be very beneficial for you. It helps you to prepare for CBSE exam, NEET, Main and Advanced. If you are new, don't forget to subscribe my channel to get the new video which will be helpful for your upcoming examination.